Hi everyone, good morning. Welcome to this YouTube live stream. My name is Wei Li and I'm product manager here at MathWorks. Today we're going to discuss a very important topic, that is how you can speed up your Simulink simulations. Joining me today are two of my colleagues, Guy Rouleau and Reid Spence. Both of them are simulation experts from MathWorks. Guy, I will start with you first. Can you give us a quick self-introduction?
Sure. Hi, everybody. My name is Guy Rouleau. I'm on the advanced support group here at MathWorks. Been doing that for 16 years. A little bit on my background. Any kind of job that I've done before working at MathWorks, I ended up using Simulink, and I always ended up at my company to be the go-to person for all MATLAB and Simulink questions, and turned out I was having more fun doing that than doing my actual job. So I decided to apply here, and I've been enjoying life since then.
Perfect. Thank you, Guy. Reid, could you do the same?
Sure. Hey everyone, I'm Reid Spence. I also work in the advanced support group, same as Guy. And similar to Guy, before joining MathWorks, I really enjoyed helping people with MATLAB and Simulink. And now I work at MathWorks and I get to do that every day, and it's great. And in particular, I've been focusing a lot on helping people speed up their simulations and also run their simulations in parallel. So I'm very excited for today's topic.
Oh, that's great. Thanks, Reid. Now, when it comes to simulations, my first impression is that there are many factors that could affect its performance. So, Guy, where do you recommend I should start?
Yep, so let's look at our agenda for today. It would be easy to start to quickly dive into advanced tools like profilers, debuggers, those kind of things. But based on all my years of helping people with Simulink, one thing that I realize is that often you get a lot more bang for your buck if you look at your higher picture workflow and you figure out how to use appropriate tools like accelerator modes, model reference, fast restart, and those kind of things. So first we're going to go through those. I'm going to describe 4 common workflows that we see, and hopefully you will recognize yourself in some of those, and that's going to help you see where to apply those tools. So let's begin with workflow 1. It's the one we call exit, update, repeat. That one, it's really when you begin to build a model, when you're making significant changes. You don't even think about simulating at this point. One thing I always recommend people when they are in that kind of workflow is to keep your model in an updatable state. And by that I mean don't make a lot of changes and then try to click play after, because if you change 17 things, you're going to get 5 errors. They're going to be all intertwined together, and it's going to be complicated to debug. So hit Control D often, make small change, Control D, small change, Control D. Obviously, when you're in that, the time that is spent is all on initialization. That's what you want to focus on. You'll see as I move to the second workflow that those workflows are in order of the evolution of a typical project. The more a project evolves, the more the model becomes stable, and the more you can build on that to optimize things. So the second workflow is going to be exit, sim, repeat. That's probably the most common workflow that you all are familiar with. In many cases, you are doing this workflow while you could do a few of the one that's coming in the next slide. In that case, you're going to look at both initialization and execution time, and often the ratio of them. I have a little picture there on the slide. Reid is going to talk a bit more about that later. Third workflow, tune, sim, repeat. In that case, the model does not change structurally. What you do is set some parameter values, simulate, see what's the impact on the result, change the values, simulate again, and so on. In that case, you really want to bring down the initialization to close to 0 as much as possible. Our last workflow, multiples simulations. In that case, you know everything in advance. You can set up everything in advance and fire a million simulation at the same time. Now that we've seen those 4 workflows, since they're important and we're going to build on that for the rest of that presentation, I want to review what they are. So, Wei-Wu, I'm going to ask you, what was the first workflow that I described?
Sure, I will give it a shot. The first workflow is the very early stage of your modeling. So at this stage, you are not doing actually simulation. You just edit and update.
Yep. Is it update and repeat?
Yes.
What's the second one?
The second is a little bit down the road with your maturity of your model. So here you actually do edit, update, and also you're going to simulate.
Yep, we call it edit, sim, repeat. Third one?
The third is as your model get a little bit more mature, now you want to actually run simulation and with some parameter tuning type of workflows.
Yep, so we call it tune, sim, repeat. In that case, you're not making any structural change to the model, just tweaking values and re-simulating to see the impact on your results. Last one?
The last one is actually you are getting more mature with your design. You pretty much lock down your design. Now you want to run a bunch of simulations. Sometimes you want to explore the design space. So multiple simulations.
Yep, thank you. So now that we've seen those four workflows, let's begin to talk about improving performance. For that, as in any kind of project, you need to capture a baseline, capture the current state, and Reed is going to help us with that.
Sure, Guy. So before we talk about capturing a baseline, let's go over some of the different simulation phases in a normal Simulink simulation. So when Guy was talking about the different workflows, he was mentioning a lot about initialization versus execution time and how that ratio is important. So a simulation in Simulink is broken up roughly into 3 different phases. We have the initialization phase. This is where Simulink is propagating signal information, it's evaluating parameters, it's compiling pieces of the model. We have the execution phase. This is what we actually think of when we think of a simulation, because the Simulink solver is running different time steps and it's calculating the outputs and the states of our model. And then in the termination phase, we do some cleanup. But the termination phase is usually really, really small compared to the other two. And that's why we say for performance, what's really important is looking at the initialization, the execution phase, and the ratio of the amount of time spent in each of those. Now let's take a look at an example at a common way that we often time things in MATLAB, and that's with the tick and talk command. Tick and talk is a great function we can use to quickly see the elapsed time spent in a certain amount of code. But let's say we were to do it as you see here in this code, where we run the sim command inside the tick and talk, and we'll get an elapsed time. But do you see maybe why there might be a problem with using tick and talk here based on what we just said about the different simulation phases? So hopefully you see that here we can only get the total time spent in the simulation, but we won't see the breakdown in the different simulation phases. And so the key takeaway for you guys here is don't use tick and talk. We can do a lot better, and I'll show you what that is now. So the better version is to use the simulation metadata. And so what is the simulation metadata? Well, first, let's take a look at whenever we run a simulation in Simulink, either from the command line or from the run button, we'll get a simulation output object, which is like that out object that you see here. And inside the simulation output object, we're going to have the simulation metadata field that's going to contain a lot of useful information for us. It's going to contain stuff like the model name, some of the settings we ran with, any warnings or errors that showed up while we were running the simulation. But of particular importance to performance, we've got the timing info field. And inside the timing info, we're going to get that breakdown of the initialization, execution, and termination time. And that's really going to be helpful for us when we go to look at what performance solutions we should choose. So the key takeaway here is a lot of the performance strategies and things that we show later on in the presentation, it's going to be really important to pay attention to the simulation metadata and the initialization versus the execution time, as we can trade off time between those two phases or maybe improve those phases.
Oh, that's very cool. Thank you, Reed. As you pointed out, the metadata is helpful to capture the initialization and execution time information. But as far as I know, Simulink provides different simulation modes that will affect the initialization and execution times. Could you take a little bit more time on that to talk about simulation modes so that I can select the right one for my simulation?
Absolutely. So let's take a look at the 3 simulation modes we have in Simulink. So I'm sure a lot of people have seen in the Simulink toolstrip, you've got your normal accelerator, rapid accelerator modes right next to the play button. But what do these actually mean? So let's take a look at normal mode. So in normal mode, Simulink is all running inside of MATLAB in what we call an interpreted mode. Because it's interpreted, it's usually very quick to start, but it can take longer to run than some of the other modes that we'll show later. So accelerator mode will actually take the model methods, basically what you've drawn in your block diagram, and it will compile that piece into a separate thing that we will run. And so because this part is compiled, it will take a little bit longer to compile, but it'll usually run faster than normal mode. And in rapid accelerator mode, we take that idea and go even further. So now, instead of just the model, we're also going to combine the solver with the model, compile them into an entirely separate process, and that'll run outside of MATLAB and communicate that with the MATLAB process. So here, it takes even longer typically to compile than accelerator, but it will typically run faster. So in each phase, we're spending a bit more time to compile in the initialization in the hopes of getting faster execution. So let's take a look at the example of how these different simulation modes perform. Guy was showing this little figure before, and now we have it a little bit larger, and we can look at more detail. So on the x-axis, we have the simulation time, basically the number of steps that we're taking in the simulation for our whole simulation stop time. And then on the y-axis, we have the elapsed time in the real world, basically the clock time. And so you'll notice that even for a simulation that isn't running for any time steps, this point where we intersect the y-axis is where this is the full initialization time, basically the time it takes just to get the simulation initialized. And you'll notice that here, normal mode typically initializes much faster than the accelerator and rapid accelerator modes because we need to do that compilation step in the accelerated modes. But as we increase the number of time steps that we simulate for, because rapid accelerator and accelerator modes run faster, the overall simulation time will run quicker. And another thing you'll want to notice is if you look at the dotted lines down here, so the solid lines represent if we've made some change to our model before we've simulated. But let's say we haven't made a change to our model since the last time we simulated. In that case, we can reuse a lot of this information that we made from the previous initialization, and we can start up much faster, and the initialization time is shorter. So let's talk about some of the different trade-offs in these simulation modes. So first consideration is that for each increase in speed, we're also usually sacrificing something in terms of flexibility, interactivity, or diagnostics in the hopes of getting better performance. So let's take a look at an example. So in normal mode, you can step through a simulation step by step, and you'll be able to see the value of every signal in your model. In accelerator mode, you can do the same thing. You can step through the simulation, but you'll notice that some signals have been optimized away in favor of speed. And in rapid accelerator mode, we can't step at all because it's a totally separate process. Also key to note is that some features are not supported in accelerator or rapid accelerator mode. Typically these will be things like things that are running interpreted MATLAB code, like the interpreted MATLAB function block. In normal mode, you can use this block just fine. In accelerator mode, you can also have this block in your model, but it's interpreted, so we can't compile that piece of your model, and that piece will still be running in interpreted mode. And then in rapid accelerator mode, because we need to compile the whole model separately, you can't have an interpreted MATLAB function block in your model. Another thing to note is that some modeling features will benefit more from accelerated modes than others. Particularly, that would be the MATLAB function block, the state flow chart, and S functions. The reason is that these blocks are compiled even in normal mode. So since they're compiled even in normal mode, and also compiled in accelerator and rapid accelerator, you may not see a big performance difference between these modes for these blocks. So if your model is almost exclusively these blocks, you may not see a big difference in performance. And finally, we'll talk a bit about this later, but accelerator mode and rapid accelerator mode will produce generated files that you can use to speed up later initializations. You may notice these SLXC files, these Simulink Cache files that will contain artifacts from previous accelerator and rapid accelerator builds that you can use for later simulations. So now let's take a look at an example to kind of rehash what we just talked about the different simulation modes. So let's say we have a model, and in normal mode it initializes in 20 seconds, and it executes in 100 seconds. Let's say we try to run the same model in rapid accelerator mode, and we notice that it initializes in 60 seconds, but it executes much faster at 15 seconds. So now let me ask you, Weiwu, let's say that we are in our edit, update, repeat workflow. We're building up our model slowly, we're doing an update diagram, but we're not actually running any simulations. Which simulation mode do you suggest that we use?
Yes, at this stage, since we are not actually running simulation, so the execution time really doesn't matter. So what I care is initialization time. So just look at the numbers. I definitely want to select the normal mode.
Yep, I totally agree. Yep, as you mentioned, even though the execution time of Rapid Accelerator is much faster, because we're not actually running a simulation, all we care about is initialization, and the initialization time of normal mode is much faster. All right, so let me ask you another question. Let's say our model is now a bit more mature, and now we actually want to run a simulation. We want to see what the results look like. So we're in that edit, sim, repeat workflow. What simulation mode do you suggest we use?
Sure, at this stage, because we actually are running simulation, so what really matters is total simulation time, including initialization and execution. So if we're going to do just quick math here, you will see the rapid accelerator mode actually will be much faster. So that would be my choice.
Yep, you're totally right, and I agree with your math there. The total simulation time is faster in Rapid Accelerator, so it's definitely worth that extra initialization time to get that benefit in the execution time.
All right, thank you, Reed, for walking us through the concept of simulation metadata and the different simulation modes. But sometimes our simulation model is not just one piece, right? It could consist of multiple components. And these components may have different maturity levels, some at the very early design phase, some others are locked down for design. So what can we do to manage the complexity here, especially from simulation's perspective? Guy, what is your take on this?
Yep. So it's time to talk about model reference now. In case you did not know, it's possible to create a simulation that is made of multiple models. I have a screenshot here. I have a top models simulation that reference 3 separate models. We have dependency analyzer who can show you this kind of dependency. We have 3 SLX files being referenced here. When you do that, each model block has an option to select which simulation mode you want to happen for this block. And if the question that, or the thought that might be coming here, yes, it is possible to use the model reference and accelerator mode to precompile and accelerate parts of a simulation. And what does that mean is that you can have at the same time in the same simulation more than one workflow. Let's look at that on one slide here. So I have this model. On the left side, I have model A and B. Those one, I'm not planning to modify them. They've been made by someone else. I'm just using them for my simulation. What I'm really focusing on is I'm editing model C. So I'm going to put a line in the middle there, and what this gives me is that I'm able to use this tune, sim, repeat workflow for A and B, where because I put them in accelerator mode, you get 0 cost for the initialization, and they will simulate as fast as possible. While on the other side, with Model C, since I'm editing at every time, I don't want to regenerate the accelerator target every time I click play because it takes time. So I'm going to have the faster initialization after making structural change on that side. Okay, let's talk a little bit more about model reference, because there are some subtle things that when you use them that you want to take care of. Big important one is the rebuild option. I've put a screenshot here. You got 4 options in terms of rebuild. The first and the last one, pretty obvious. Always, every time you will click play, all your model reference in accelerator mode will regenerate code. Never. We're going to close our eyes. We're just going to use what has been pre-compiled, even if your model has changed. So the 2 in the middle, a little bit more tricky. In the documentation, we have this diagram here. The one important piece that you want to look at is this one here, is the structural checksum has changed. It's important because it's taking time. It can take as much time as initializing the model in normal mode. I like to resume to the key takeaway from this diagram is that if you pick if changes are detected, every time you click play, we will recompute this checksum to be 100% sure that we will rebuild if it needs to. With the option, if changes in known dependencies are detected, we're going to first look at the timestamp of the cache file. If the timestamp is consistent with the model, we're not going to do the checksum and we'll immediately use the precompiled artifact. So it's much faster. So if you rebuild, you want to go where that green line is to skip the structural checksum. If you want to read more on that, I have published a post on my blog on that topic just this week, covering that in more details. Simulation cache, we've been talking about it for some time. What does it look like? It's a file with an extension SLXC. You will see appearing next to your model with the same name as the model, a file with the .slxc extension. If you double click on it, it's going to show you a report showing what is inside that cache. And the cache can contain multiple things. It can contain artifacts from multiple operating systems. It can also contain the precompiled stuff for different targets, for the accelerator mode, the rapid accelerator, for model reference. Once you have, even if you have your setup as optimal as possible, or your cache, it's going to happen every once in a while that you need to rebuild everything or rebuild many of the reference model. If that's your case, parallel build can help with that. If you have parallel computing toolbox, you check that box, and many MATLABs will be fired under the hood to build all those reference models in parallel. That's if you want to build everything on your machine. The next step to escalate after that is to leverage your CI system. More and more companies have nice CI, continuous integration setup those days. I like this picture from our documentation. Think about that. You have a big model that contains 100 or 1,000 reference model. For yourself, it's very likely that you will work on only a small number of those. You make your change. At the same time, you got colleagues who work on other models making change too. Well, if everyone commit their design change, their SLX file to the source control system, overnight, your continuous integration can build all that, build all the reference target. You can set that up to build for different OSs if different teams members are working on different operating system. That way, when you come in the morning, you don't even need to build the accelerator target for the models that your colleagues have changed. They will be pre-built, they will be shelved by the CI system, and you will just pull them from there. I'm going to tell you a real story here. A few months ago, I received a big project from one of our customers that I needed to debug something with. The first time I got it, that thing had 1,000 model reference. I fire 8 parallel worker and he built a parallel build. Took 6 hours to build everything. Once all the cache was made, the second time I click play, the time it takes between I click play and the clock start to increase in the simulation took only 30 seconds. So that's definitely worth investing in that if you have this kind of large model. I think I covered most of what I wanted to share for model and reference tips.
Thanks, Guy. The number you just showed, the speed up is really impressive. I just want to say there's a very good techniques for speeding up the initialization time while building up a model. But let's say I'm not making any changes to my model. Do I still need to run the model initialization every time? Reid, what are your suggestions on this?
Sure, that's a really great question, Weiwu. So first, I want to ask, have you ever noticed the fast restart button on the Simulink tool strip? It's right up there next to the play button, and you might wonder what that is. Well, this is a really great, useful feature for the situation, Weiwu, you were describing. Basically, it's useful when you want to simulate a model iteratively without making changes in between it. And so the way that it works is that when you turn fast restart on, the first simulation you run on that model, it'll compile the model the same way it does when fast restart's off. But the key difference is the model will remain in the compiled state for the next simulation, which means that we can restart the simulation very quickly, thus fast restart. And the way that we're able to do this is that while fast restart is on, you won't be able to make structural changes to your model, so you won't be able to do things such as add or remove blocks. If you open up certain blocks, most of the parameters you'll be able to change, but you'll notice that some parameters you won't be able to change, as you see grayed out here. Just to show you some of the power of fast restart, here's an example of using fast restart, using the use fast restart option and the sim command. So you can see here where the first simulation, we need to update the model and it takes about 5 seconds. But the second simulation, we keep the model in the compiled state and we can quickly restart it almost instantaneously. So that happens in fractions of a second. And so as we were saying, this feature is really useful for those tune, sim, repeat, or multiple simulation workflows where we're not going to be making a lot of changes to our model, but we're going to be running a lot of simulations. So a key thing about fast restart is there isn't a fast restart for Rapid Accelerator, but we have something similar. So in order to explain that, we first need to know that when you run a Rapid Accelerator simulation, by default, Rapid Accelerator will compute a checksum of the model. Basically, that means we're looking for changes in your model since the last time you built the Rapid Accelerator model. This doesn't take as long as rebuilding the model again, but it does take, and it can take a significant amount of time. So if you know that you're not going to change your model between runs of Rapid Accelerator, you can tell Simulink to skip this phase entirely and save some time. So to do that, you can use this parameter that you see here called Rapid Accelerator UpToDate Check. You can turn that off and tell Simulink, trust me, I haven't made any changes. Just reuse what you've previously built before for Rapid Accelerator. So here we're running 3 simulations of Rapid Accelerator, and you can see the timing of each here. For the first one, we need to generate code from the model and build it in Rapid Accelerator. That takes a good bit of time. It takes about 3 minutes here. The second time, we don't need to rebuild, but we still ran the check to make sure that the model hasn't changed since the last time. The check takes a couple of seconds. The third time, we turn off that UpToDate check. We just say, Simulink, trust me, use what you had built before, and we can restart the simulation again almost instantaneously.
Wow, that's great. We know there's a way to work with the Rapid Accelerator mode as well. So now I know how fast restart can help me skip the initialization stage, but sometimes I'm dealing with a large number of simulations, for example, thousands or even more. Are there any techniques to accelerate those type of workflow?
Definitely, Wei-Wu. So in Simulink, we've got 2 main functions to help you run your simulations in parallel, which will be much faster than running them in serial. And those functions are parseSim and batchSim. And the main difference between parseSim and batchSim, so in parseSim, we're going to open up a connection between the client MATLAB, that's basically the MATLAB you have open on your computer, and the workers that'll be running the simulation. And that connection is maintained throughout as the simulations run, so you can see the simulation results live and you can see the status of those simulations. In batchSim, it's a bit different. You would package up all those simulations and send them off to the workers all at once. One of those workers will be designated the head worker, and that will distribute those simulations across all of the other workers. But during this time, you're not continuously connected to the workers from your client, so you can disconnect your computer, and then you can let it run in the background. You can do other things on your computer, on your client MATLAB, and then once the simulations are done, you can connect back again to the workers and pull the results back. And so because you don't need a continuous connection between the client and the workers, batchSim is most commonly used for connecting to external clusters like cloud platforms or high-performance computing clusters, where you might not have a stable connection to those workers. And parseSim is really popular for when you want to run a lot of simulations on your local machine. You say you have multiple cores and you want to run a bunch of simulations on all those cores. And so a great thing about the parseSim and batchSim command is how they automate the setup, the cleanup, and the visualization for you for these parallel simulations to make it as easy as possible to scale from serial to parallel. So for example, parseSim and batchSim will do a dependency analysis check to find all the files that are needed by your model and automatically send those to the workers so that it can run. You also have the option to package up the base workspace variables and send those to the workers. And then once all the simulations are done, parseSim, batchSim, they'll clean up all of the files that are generated. They'll send all of the results over to your client. And then we have a nice feature called Simulation Manager, which you can use to kind of monitor the status of the simulations as they're running and also get a live update of the results and review the results once they're done. So here's just a quick example of kind of the power of parallel simulation. So I have this model and I want to run 1,000 simulations on it. And I know that on my machine I have multiple cores. So in typical serial simulation, I would just be using one core to run all these simulations, but I have a lot more. So if I use parseSim, I can open up multiple MATLAB workers. As you open up the task manager here, you can see I'm getting almost 100% CPU utilization as I'm using all of those cores. I'm running the simulations a lot faster.
Well, that's great. Thanks, Reid. parallel simulation definitely is one of my favorite features for simulation performance improvement. So far, we have seen a lot of techniques that could potentially be useful for your simulation. But sometimes we have tried everything, including the techniques we just talked about here. We're still not super satisfied with the performance and really want to have a deeper look to the model to identify the bottlenecks. What are your suggestions on this?
Sure. Yeah, that's right, Wei-Wu. As you mentioned, up until now, we've been talking mostly about the larger workflow and some of the different settings we can apply to a model, but not actually the model design itself. And what if we want to look into different bottlenecks that might exist in our model design? So in Simulink, we've got quite a few tools to do this, and we're going to cover 5 of them today. So first, let's start with the Performance Advisor. The Performance Advisor is a great place to start for the beginning of any performance investigation into a model. You can quickly access it from the Debug tab in the Simulink tool strip. And what the Performance Advisor is that it's a set of automated checks that you can run on your model for different settings and modeling patterns that we know can affect performance of your model. And so when you open up the Performance Advisor, it's going to look like this. It's going to have a set of checks, and you have the option to, for instance, run all those checks in a single click. You can also choose for Performance Advisor to fix any improvements that it finds automatically, or if you notice that you maybe don't want to allow it to automatically fix it, but you still think you want to review the change, you can apply the fix with a single click. And also you can see a report of all the changes and checks that were run for later review. So just to give you a quick example of something Performance Advisor can help you with. So Guy and I were helping a customer the other day speed up their rapid accelerator simulation. And one of the first things we had them try was to run the Performance Advisor. And the Performance Advisor found one particular model setting that, when changed, actually improved the simulation time by 2 times. It cut it in half. And so that model setting was this compiler optimization setting that you can actually change for Rapid Accelerator when we're compiling that Rapid Accelerator model. And so even Guy and I will forget some settings, and the different settings can have different effects on different models. So it's always a good idea to try the Performance Advisor. All right, now let's switch gears a little bit and remember one thing, and that's that Simulink and MATLAB are connected. So Simulink sits on top of MATLAB. And that means for most models in Simulink, they should be running mostly in the Simulink engine, but sometimes Simulink can trigger MATLAB code to run. And it can trigger things to run through callbacks, for instance, on models or blocks or mask. Or maybe we have some blocks that are running interpreted MATLAB code, such as a MATLAB function block with an extrinsic call, or interpreted MATLAB block. So it can be a good idea to turn on the MATLAB profiler when you run a simulation, as you see in this code here. And then we can use the profile viewer to see the type of MATLAB code that's being triggered by our simulation. And what we want to look for is code that's outside MATLAB root, basically stuff that's not MATLAB source code, but maybe code you've written, code a colleague's written, code that a third party has written, and see if that's taking up a significant amount of the simulation. If it is, we might want to look into why that code is being called and see what we can do to maybe improve its performance. And one big way that Simulink can call MATLAB code is through callbacks. And if you notice that there's a lot of callback code is being called by your model, you might want to try the callback tracer, which you can find from the Debug tab in the tool strip. The callback tracer is going to show us a lot of the same information that we saw in the MATLAB profiler, but it'll show us more detailed information for callbacks that help us debug them. So for instance, it'll show each callback, it'll give us a hyperlink to the code of that callback and also a link to the block in the model that's calling it. We'll also see a breakdown of the time spent in each of the callbacks. So I've been talking about all the different ways you can profile the MATLAB code, but what about the actual Simulink model itself and the Simulink engine, the Simulink solver? Guy, can you tell us a little bit of tools we can use to debug that?
Yep. So for the Simulink core performance issues, we have 2 types of profiler, the Simulink profiler and the solver profiler. I put together this flowchart here that I think helps figure out which one to use when. The first decision point that I like to classify performance problem is it something that one block in particular in your simulation or a group of blocks is taking more time than the others or than you expect? Or is it that the simulation is using a variable steps solver and it's taking too many small steps and capturing a dynamics faster than what you want to simulate. So with a variable steps solver, I would go with the solver profiler, and with the fixed step, if it's a fixed steps solver, I would start with the Simulink profiler. Let's look at the Simulink profilers first. As I said, mostly useful for fixed steps simulation. You enable it from the debug tab in the tool strip. When you click play, at the end it's going to pop up a panel that's going to look like that in your canvas. And you will see a hierarchy that is the same as the subsystem in your model. And you will be able to see the timing. It's going to be ranked by the most expensive one at the top. Based on that, if you identify a block that takes more time than you expect, now it becomes your job to decide if you want to simplify it, find whatever way to improve the performance of that specific block. When you're using the Simulink profiler, I recommend to also launch the property inspector. It's going to give you a finer breakdown of the different methods executed by this block and can give you some insight information. The second tool that I'm talking about is the solver profiler. This one, in the main panel, it's going to plot the step size over time. And there's a dash line at the top with the max step size at which Simulink might be able to step. If you're taking steps smaller than that, like you can see at the beginning here, you want to look in those tables below. We're going to bubble at the top of the table all the reasons why the solver is taking steps smaller than the max step size. Those can be things like solver exception, which the solver will sometimes it will try to take steps larger and it will exceed the tolerances that you specify in the model configuration. So to respect your tolerance, you might take smaller step. There's also zero crossing to capture discontinuous event. There's solver reset that are necessary when some kind of event happen in simulation. So it will help you understanding why the solver is taking the step that it takes. This tool is especially useful for Simscape model and anything that is variable step, it can definitely help. I'll bring back that flowchart again just to make sure it's there. Fixed steps solver, you can go straight with the Simulink profiler. If you have a variable step solver, first look at the solver profiler, see if that step that it takes makes sense to you. And if it does, then you can look at the Simulink profiler to see if there are some blocks within one time step that's taking more time than you expect. So I think that's what I wanted to say for those two profiler.
Wow, we definitely have gone through quite a lot today. Now let's wrap this up with a summary of what I believe should be your key takeaways. We covered performance from two different lenses. The first is how we can change our workflow and settings to optimize performance. The second is how we can dig into the details of our model to look for performance bottlenecks.
That's right, Weiwu. So as you mentioned, at first we looked at the larger picture, the workflow and the settings around our model, how we can change those and often get big performance improvements without having to actually change the model itself. So in particular, we talked about the simulation metadata, how we can use that to measure the initialization and execution phases of our model, and how that can be really important to deciding what to do about performance later on. We talked about the three simulation modes in Simulink, normal, accelerator, and rapid accelerator, how accelerator and rapid accelerator speed things up by compiling pieces of our model. The compilation can take longer, but it can give us much better execution time performance. And also we talked about model referencing, how we can use model references to split up pieces of our model and run them in different simulation modes. So the pieces that we aren't changing, we can run in the accelerator modes, and the pieces that we are changing, we can run in normal mode. We also talked about the Simulink Cache and how we can use the Simulink Cache to speed up the initialization of our simulations and maybe even share them across our organization to speed up simulations for a large group of people.
Then we went into tools to understand the performance of one simulation. I decided to put the three most common one here. typically, Simulink should not run a lot of MATLAB code, but it can. So just try the MATLAB profiler. It's easy. It's going to tell you if undesired MATLAB code is running. Then we talk about the Simulink profiler, which is especially useful if you have a fixed step simulation and want to see the cost of each block within one time step. And then we talk about the solver profiler, who can help you to understand why the variable step solver is taking the step that it's taking.
Okay, this is a really helpful discussion. Now, before we transition to Q&A, I want to let you know that we have a technical article on the MathWorks website that covers the same, or at least very similar topics. Once we're done here with this live stream, if you want to read more on this topic and get hyperlinks to the relevant doc pages, I highly recommend you go to read this article. And one more thing, in case you don't know, Guy has a very famous and popular blog, Guy on Simulink. From time to time, he publishes useful performance-related tips and tricks on his blog. So this is another thing I highly recommend that you check out and subscribe if better, so that you can receive additional information. So now it's really time for Q&A. Let's see what type of questions we had so far. We already have, I think, 3 questions I want to ask you guys. The first one is, can we discuss the performance difference between MATLAB function and system blocks, if there's any, regarding speed, resource, and ideal application scenario? I think this is very, very big topic. I don't know how much time you can. Yeah,
I can take that. I can spend a minute or two on that. So we have more than one block to include MATLAB code in a simulation. The 2 big ones are the MATLAB function block and the MATLAB system block. As their name implies, the MATLAB function is a function. It takes input, generates output. It's called that once every time step. This block typically gets compiled, whether it is by generating code and generating a MX file or generating an execution engine in memory. The MATLAB system block, it offers more possibility to do more complex things. It can have more than one method in addition to the output, can have update, derivative, those kind of things. By default, it can also generate code or generate an accelerator target in memory. So by default, they can run both at the same speed. The MATLAB system block has an option in its dialog that you can specifically ask to have it run in interpreted mode. That way you can call any MATLAB code that does for which you cannot generate code out of it. For example, you can plot things, and if you run it in interpreted mode, then the MATLAB system block will run significantly slower. I think that's the key.
That's a good summary.
Thanks, Reid. I know this is big. Maybe it could take another 45 minutes just to talk about this, but that's a good summary. The second question is on parsing. I think, Reid, you might be able to help this. The question is, which variables can we change between different simulations? Could we change variables that are initialized into MATLAB code before running simulations?
Yeah, so you can change, in general, you can change any variable you want in a parallel simulation. We talked a little bit about the difference between tunable and non-tunable parameters. So in general, you can change any of those parameters in parsim. If you're just changing tunable parameters, then you can use fast restarts, and that'll help run different iterative simulations really quickly. Regarding using a MATLAB script or code to initialize variables, in parsim and batchsim, there's the idea of a setup function, also a presim function. So in here, you can put any code you want to run, basically on the workers. The setup function runs once per worker, the presim function once before each simulation. So if you have some specific code that you want to run, you can use those functions to do that. Otherwise, you can put all of your different variables you want to change inside the simulation input object, which is a really great container for all the simulations you want to run.
Perfect.
I think it might be worth you mention retunable versus non-retunable. We mentioned the concept a few times of the structural changes. So I think it might be worth to add a few words on that. between two simulation, if you manually change the model, add blocks, delete blocks, obviously it's a structural change. There are also the possibility that you will change the value of a parameter and it will result in a structural change. If you, for example, you call parsim and you wanted to run different values for a gain block, that we don't need to rebuild. It's not a structural change. It can go super fast. If you change the dimension of a signal, if you change the sample time of a signal, those are considered structural change. So in that case, you will not be able to reuse your pre-built artifact. We're going to need to regenerate the accelerator, the target between each simulation. It's going to work, but it's going to take longer to happen.
Yep.
Perfect. So we have another question popping up right now. We talk about lots of acceleration strategy, but this customer looks like is specifically interested in data flow. I remember we discussed that in technical article. We didn't present it here.
Yeah.
I'm not sure whether you have a very short summary on that or just ask them to read the technical article.
Data flow is something that is targeted mostly for signal processing applications. It allows you to mark a subsystem to be the data flow domain, and in that case, we're going to analyze it and be able to run on multiple thread parts of the algorithm in there. Like if you're doing signal processing, there are FFTs, correlations, things like that. We'll be able to optimize that to use multiple core on your machine for one single simulation.
Perfect. And again, if you want to get more information, definitely check out the technical article. It provides more information there. Now, I think, Guy, we talk about different modeling techniques there. The one question we heard from the audience is if you compare model reference, library, and subsystem references, what are the major differences, or are there any differences in terms of simulation performance?
Yes, sure. So those three different technologies, model reference, subsystem reference, libraries, are three ways that you can componentize your model. If you work on a team, you can have different contributors saving their work in the different files and have all that combined into one simulation. Model reference is really the one that will help with performance, because model reference, the unit is a model, it's a standalone unit that we're able to compile by itself, make it accelerated, and reuse caches, since it's one atomic unit. Subsystem reference and libraries, it's different kind of thing. For subsystem reference, the mental model that I like to use is you just want to save the content of a subsystem in a different file. You want to save the blocks or how they are connected into a separate file, so you don't have source control merging conflicts. But it's not going to help in terms of performance of one simulation. Libraries, I recommend using libraries if you're going to make, for example, a toolbox made of small utilities that will be distributed to many users and that will not change frequently.
Yeah.
And we have a link in our article and in the documentation where you have a clear table with 3 columns with the plus and deltas and the application of each of them. Yeah. It's worth definitely reading that.
Yeah, and I want to point out also a lot of the performance strategies we talked about in the presentation, like parallel build, the ability to change simulation mode, those are only possible with model reference because of the model reference being more encapsulated than the library and subsystem, right? So all the things we presented, model reference gives us the power to do those things.
Model reference, it gives more power, but sometimes it comes with more constraint. Subsystem reference is more flexible, so there's always a trade-off.
Yeah. So now, Rita, there's one very interesting question here. Is can you change simulation modes in the middle of a simulation?
So currently you're not able to change the simulation mode in the middle of a run. But one workflow we often see people do is maybe they want to do some debugging and they want to get to a certain part of their simulation much quicker. One feature we didn't show today but is very useful for that sort of thing is operating points. And basically what you can do is you can save an operating point for your model at a particular set of time, and then you can load that operating point into your model and you can just restart your model right there at that time step. with all the states initialized to the same thing they were at that operating point. And then that'll help you quickly skip a large section of your simulation and debug at that point.
The classic example that we like to use for that is, let's say you want to simulate an aircraft doing some maneuver, but all your simulation starts with the taking off and then reaching a steady rate at a certain altitude. You save your operating point, and then from there you diverge your different maneuver.
That's a good one. It's not a typical you would change, but definitely I can see the usage for some cases. So the last one I want to take here is we have seen techniques to run multiple simulations in parallel, but is there any specific features, techniques we can parallelize a single simulation? I think we touched a little bit on the technical article. We didn't have time to cover today, but Reid, what's
We talked a little bit about data flow. That's one of the features that we talk about in the technical article. There are some other features that we also talk about in that article for running particular parts of your model on multiple threads. So we have some support for that sort of thing, whether it be S functions, FMUs, and model reference. But in general, you usually find a much better performance increase by moving to parsim, batch sim, running multiple simulations across multiple workers. You can scale up your simulations much faster that way.
Yeah, I think there's no single answer for that, right? So there's multiple techniques you could apply. Depends on what simulation model you're dealing with.
Those kind of features for the multi-threaded, they can be useful if you have one component that has a lot of computation inside, exchanging only a little bit of the data. Otherwise, there is some overhead that always takes over. And even if you're using a separate thread, at the end of the day, in the big picture, it doesn't give that much of a speed up based on our experience.
Exactly. So I think this might be the last one, the real last one for the whole live stream. Funny enough, this is not really on performance side, but Guy or Reid maybe give a take. So the question is, on the Simscape side, they're using the specialized power system, and the customer tried to convert it to model reference and had some problems. Is that a known issue, or is?
So all the Simscape technology, you can place an entire Simscape network inside a reference model, but you cannot cut a Simscape network in. You cannot put parts of a Simscape network inside a reference model and and another part of the network in a different model and reference. Since the Simscape unit is seen as one atomic unit, it's not possible to componentize it like that. You can save parts of a Simscape network into the different subsystem reference file. That helps with different person on your team working on the same model, but that's not going to help with the speed up. If you want to do something in the Simscape library, we have a section that offers a set of blocks that are called network couplers that will help going out of Simscape to Simulink and back to Simscape again. And by using those couplers, then you can split your Simscape network into two networks and place each of them in a separate reference model.
Perfect. Thanks, Guy. And since our time is running up now, I think we want to conclude the Q&A session right now. But if you have further questions, please just leave your question in the chat window. I think we'll read them after and hopefully send you some useful information. Again, I think we had a very great discussion today, and hopefully you have learned something useful. And I want to thank you again, Reid and Guy, for this nice sharing. I think we'll stop here, and thank you very much for listening. Hopefully to see you next time.
Thanks, everyone.
Thanks, everyone.
Thank you.